Hello, everyone. Welcome for our CIC webinar, Center for Integrated Catalysis. And today it's my great honor to introduce our speaker, Professor Brookhart. So Professor Brookhart received his PhD degree in physical organic chemistry at UCLA in 1968. And after his PhD study, he was NSF postdoc fellow at USC, and then followed by another postdoc at Southampton University. And Professor Brookhart joined University of North Carolina faculty in 1969, and he retired as a Williams R. Kainer Jr. Professor of Chemistry in 2014. And in 2015, he joined the faculty at University of Houston to conduct joint research. And Professor Brookhart was the associate editor of the journal Organometallics. He has received many awards, including but not limited to ACS awards in organometallics chemistry, polymer chemistry, and he was also elected to the National Academy of Sciences in 2001, and the North Carolina Award in Science in 2008, and then the Willard Gibbs Medal in 2010. Professor Brookhart's work spans on mechanical, mechanistic, synthetic, and structural organometallics chemistry, as many of us know, and also catalysis. And a lot of his work focus on the development of late transition metal complexes for olefin polymerization and also carbon hydrogen, silicon hydrogen bond activation. So today he's going to give us a talk on his work on the development of those metal catalysts for synthesis of polyolefins. So let's welcome Professor Brookhart.
I hear thunderous applause out there.
We're all muted.
Yeah, you're all muted. That's what okay, can everyone hear me? I assume so. So away we go here. This was supposed to be, I asked to give a tutorial kind of talk. And let's see, I'm trying to get rid of people's faces. Okay, that's gonna be okay. So what I thought I would do is talk about basically how we developed late metal catalysts for olefin polymerizations, some of the simple ideas that led us into developing these catalysts, and that's going to go back quite a ways to some fairly ancient chemistry. And I really want to focus on polyethylene. Polyethylene is the largest volume polymer produced worldwide, and this just gives you a feeling for how much we make. In 2018, we were making 100 million metric tons, valued at $164 billion. And you can see there how it's divided up by region. As we'll see on the next slide, polyethylene has some ideal properties. So you can see on the left of the slide, it has multiple uses. You can make films from it. You can injection mold it. You can extrusion. You can blow mold it. You can make wires and cables from it. So there are enormous numbers of applications of this polymer. If you look under your milk jug, you'll see a 2 for recycling. That's high density polyethylene. Polyethylene is a semi-crystalline thermoplastic, and I'm sure those of you that have had a polymer course, this is going to be very simple, but maybe I should at least describe what that is. We have crystalline domains in the polymer. It's about 70% crystalline domains, and the TM of the melting point of these domains is around 136 for high density polyethylene. The crystalline domains are connected through amorphous materials, and those amorphous materials have a glass transition temperature of about minus 125 C. So you've got an enormous workable range. You know, once you go below the TG, the material becomes brittle, but between the TG and the TM, you've got a workable range, and you can see that's quite enormous. So it has, polyethylene has very high impact strength. If we're completely crystalline or below the TG, it would have strength, but it wouldn't have impact strength. Since it's a hydrocarbon polymer, it has high chemical resistance to acids, base, oxidants, and solvents. It's a good insulator. So as I mentioned on the previous slides, it has many, many applications. So there are several grades of polyethylene, and in addition to high density polyethylene, there's so-called linear low density polyethylene. This is a material that's lightly branched, and so the TM is reduced from about 135 down into the 115 to 130 range. The branches along the chain make this material more flexible, less crystalline. Primarily, this would be used, for example, for garbage bags, grocery bags, saran wraps. And there's low density polyethylene, which is more highly branched with an even lower TM, and I'll show you where that comes from in a minute. There are other grades of polyethylene. There's ultra high molecular weight polyethylene that's usually spun into fibers for bulletproof vests. It's also used for artificial joints. If you get a hip replacement, you're likely to get a polyethylene hip. Then there are polyethylene copolymers, which involve copolymerization of ethylene and functionalized vinyl monomers. And these have some special properties with regard to barrier properties, adhesive properties, ability to cross-link these chains. So that's another important type of polyethylene. So most polyethylene and polypropylene, for that matter, is produced commercially using early metal systems. You can use Phillips catalysts, which are basically chromium-based catalysts, chromium supported on silica. You can use Ziegler-type catalysts involving titanium halides activated with aluminum alkyls, and a lot of polyethylene is now made using these so-called metallocene systems. The mechanism of polymer formation using early metal systems involves generally activation of some metal halide to generate a metal alkyl. And then the propagation step goes by a so-called Kase-Arlman coordination insertion mechanism. So we generate some sort of metal alkyl, we bind ethylene, we do migratory insertion to build up the chain. This new metal alkyl binds another ethylene, another insertion, and so on, and we grow a chain. The resting state in these systems is the metal alkyl. The alkyl olefin species is never observed. The molecular weight in these systems is often limited by chain transfer processes, and the most common one is chain transfer through beta elimination. So as the chain grows, the beta hydrogen can be transferred to the metal to generate an olefin hydride. This unsaturated chain drops off. The metal hydride starts a new chain. The other way we can do chain transfer is through hydrogenolysis. So we expose this system to hydrogen, we can clip off the chain and make a metal hydride and start a new chain. So the average degree of polymerization is simply the rate of propagation over the rate of chain transfer. The low density polyethylene is often made through a radical process. So we have some initiator here, often an alkoxy radical. These reactions run at extremely high pressure and high temperatures. Ethylene is not very reactive towards radicals. You're generating a primary radical, but obviously you can add to generate a primary radical that adds another ethylene and so on. And that radical can do backbiting. So for example, this radical can abstract a hydrogen atom further down the chain and generate a secondary radical. And this leads to highly branched polyethylene with lower melting points. Okay, so I want to switch now to gears quite substantially and show you some of our thought processes and how we actually got into doing late metal olefin polymerizations. we were back in the early 80s, we, along with Malcolm Green, were discovering systems that exhibited so-called agostic interactions, where a CH bond of a remote on some remote site of the ligand interacts with the metal center and serves as essentially a 2-electron donor ligand. These agostic species exhibit long CH bonds. It's a weak interaction. That CH interaction is easily displaced. The CH frequency is low. In the NMR spectrum, typically the CH bond exhibits high field chemical shift. And these, since this is a weak interaction, these are highly dynamic. So there's rapid exchange between HA, H1, and H2. An example here that I'll show you more about later comes from simply the protonation of a cobalt ethylene complex, this cobalt-1 species, to generate an ethyl agostic species in which the beta CH is bridged back to the cobalt center. It's not an ethylene hydride, but an agostic species. So this next slide is really the key to how we thought about getting into late metal olefin polymerizations. If you recall, when we grow a chain, we generate an olefin alkyl, do migratory insertion, and the chain continues. The classical view of an olefin hydride is a terminal hydride, and we have migratory insertion through a bridge transition state to generate the unsaturated metal alkyl. So if you think about the migratory insertion, sorry, I got to turn my phone off here. If you think about a migratory insertion, the corresponding migratory insertion of a metal, say a methyl complex, that barrier is a lot higher than the migration of hydrogen. The bridging alkyl is much less stable than the bridging hydrogen. So now imagine if we choose a metal and ligand combination so that the bridging hydrogen becomes the ground state of the species, the most stable form of the species, then the barrier to alkyl migration in that same species should be lowered. And so if we pick out a system in which the metal hydride is agostic, we would propose that the barrier to methyl migration in the same analogous species should be a lot lower. And so that's illustrated here. Here's the most stable form of the agostic species. Then the barrier then should be a lot lower relative to one in which the hydride is classical. And so we propose that if we generate an agostic ethyl species and expose it to ethylene, we should displace the CH interaction to make the alkyl olefin complex. This should undergo migratory insertion to generate a new agostic species with a butyl chain that can bind ethylene and so on, and we should be able to generate polyethylene. So the system we're going to test is exactly the cobalt system that I showed you on the previous slide. We take this cobalt ethylene species, protonate it, and generate an agostic species. And in fact, if you expose this agostic species to ethylene, in fact, you grow a polyethylene chain. We were able to actually observe the ethyl ethylene species using C13 labeled ethylene and actually see the barrier to migration. It's about 14 kilocalories per mole. And then we can actually just watch the chain grow. We get linear polyethylene, but it's a low molecular weight and it has a fairly short lifetime. And we proposed that the lifetime was limited by the counterion. BF4 was known at that time to be a fluoride source. And so we expected that this highly electrophilic cobalt-3 species was simply being quenched by BF4. So we sought out a more unreactive counterion and decided to use this Kobayashi counterion, commonly known, you probably now know it as the BARF counterion, this species, this tetraaryl borate species here sprinkled with CF substitute with CF3 groups. And we were able to make an acid of that species by simply taking the sodium BARF, treating it with HCl and ether, and generating the etherate BARF salt. So using that acid, we could generate the cobalt species with the BARF counterion. And if we now looked at the lifetimes of these species, if you looked at the BF4 salt, it had a half-life in methylene chloride of about 30 minutes. If we used the BARF salt in methylene chloride, the half-life was about 7 days. And as it decomposed, we formed the chloromethane. We then turned it to chlorobenzene. And in chlorobenzene, the BARF salt has a half-life of more than 30 days. So that solved the stability problem. The other advantage of BARF is that the salt is extremely soluble. So we can do very low temperature NMR spectra of these species and really see a lot of detail. So to skip ahead, well, no, I should not too far. So we decided to think about other late metal systems. And if you go to the literature, you find that in the early 80s, Shell developed a so-called shop process in which they used a neutral nickel system to oligomerize ethylene and make these series of alpha olefins. The fact that we generate alpha olefins here means that the rate of propagation is roughly the rate of chain transfer. So we don't get polymer, but we do get more than dimer. And these alpha olefins are quite valuable for precursors to detergents and oil additives and so on. These were neutral systems, and we realized that if we had cationic species, they're going to be much more electrophilic and more likely to exhibit lower barriers to migratory insertion. So to skip ahead a bit, we looked at a number of nickel and palladium systems, and Linda Johnson discovered these alpha diimine systems. So she synthesized a series of these. If you don't have these ortho, alkyl, or aryl groups on this species, you do generate oligomers, just like the shop systems. On the other hand, if you put bulky groups at these sites, you generate high molecular weight polymers, and as I'll show you, they have quite unique microstructures. We can polymerize ethylene or alpha olefins or various cyclic olefins, trans 1,2 disubstitute olefins, and we can copolymerize ethylene with certain polar vinyl monomers, and I'll show you a little bit of that chemistry later. So on the next slide, I'll summarize the kind of polymers that we make. Recall that with early metal systems, when you polymerize ethylene, you get strictly a linear semi-crystalline high density polyethylene. And if you want to put branches in, you have to copolymerize ethylene with an alpha olefin like 1-octene or 1-hexene to sprinkle branches along the chain and reduce the TM and the percent crystallinity. What we see with the palladium systems is that when we polymerize ethylene, we can get high molecular weight material, and it's hyper-branched. You see highly branched materials. They're branches on branches. It's completely amorphous. They're anywhere between 100 and 110 or 20 branches per 1,000 carbons, depending on exactly which substituents you choose. In the case of the nickel, we've made well-defined catalysts, but an easy way into the systems is to simply take the nickel dibromide and activate it with diethyl aluminum chloride or other metal alkyl aluminum activators. These systems are extremely reactive. So they turn over about anywhere between 1 and 3 million turnovers per hour, as opposed to the palladium, which turns over very slowly at say 500 turnovers an hour. And you get more lightly branched materials. The TMs can range from 25 to 135, depending on the branching. We can see 5 to 80 branches. And what we see is that if we increase the ethylene pressure, we decrease the branching. And if we increase the temperature, the branching increases. So we can control the extent of branching simply by temperature and pressure. Now on the next slide is several years worth of work all summarized in one slide here. As I mentioned, these catalysts were discovered in our lab by Linda Johnson and Chris Killian and John Temple and Steve Zveda and Hoff and Leatherman all contributed to understanding this whole mechanistic picture. So I'm going to take you through that fairly slowly. You can observe the resting state by NMR spectroscopy, and the resting state of the catalyst is the alkyl olefin species. The turnover limiting step is the migratory insertion. So unlike early metal systems, the rate of chain propagation is independent of ethylene or alpha olefin pressure, but it's only dependent upon the rate of migratory insertion. It turns out that the ratio of the rates of the nickel insertion to the palladium insertion is about 7,000. So the nickel, as we've seen on the earlier slide, is far more reactive than the palladium system. Once this undergoes migratory insertion, indeed you generate the agostic species, the beta agostic species. And the reason you get branching is that this can beta eliminate and reinsert, and the metal walks 1 carbon down the chain. So this is a primary attachment. It marches 1 carbon down to generate this species, a secondary species with an alpha methyl group. If this binds ethylene and inserts, you put a methyl branch in the chain. If this walks another carbon down the chain, now you have a C2 branch. If this binds ethylene and inserts, you put an ethyl branch in the chain. Now, in the case of nickel, once this agostic species is trapped by ethylene, it's irreversible. So as you increase the ethylene pressure, this species gets trapped earlier and earlier in this chain running process. And so at high ethylene pressures, you basically sit here and generate almost linear polyethylene. As you lower the pressure, you see increasing methyl branches. And as you lower the pressure further, you can see ethyl branches and longer branches. In the case of palladium, this is reversible. And so even though it traps, it comes back to the agostic species and can run again, trapped, back out, and run again. And so what we find is that the palladium can walk over 200 to 400 carbons before it ever finishes off with an insertion process. So that's why you get these extremely branched materials. And in fact, this can run through a branch. So it can run down, put in a branch, come back, and then insert and run through that branch and put a branch on a branch. So this was all done by a series of very careful low temperature NMR experiments and a lot of polymer analysis. So that summarizes a terrific amount of work on the part of these folks shown on the slide here. So the key here, I should have mentioned that, I did mention that. If we go back here, if these substituents aren't large groups, then we simply get oligomerization. So by putting these large groups on here, we're effectively changing the rate of propagation relative to chain transfer. And if you look at the crystal structure of one of these substituted diimine systems, these ortho substituents lie over the axial sites. And that's key because we postulated that in these D8 systems, chain transfer does not occur by dissociation of the unsaturated chain, but an associative displacement reaction, as is typical for these D8 metal systems. So if we block the axial sites, we retard that rate of chain displacement. We don't affect the rate of migratory insertion. So we simply, even though we access this olefin hydride, the olefin doesn't insert it because it's blocked from a dissociative displacement. Now, Ziegler has suggested that chain transfer may come from the olefin alkyl species in a process called chain transfer to monomer, where hydrogen shifts to the unsaturated species, in this case ethylene, to generate a bis-olefin hydride complex, and that by bulking up the axial sites, this barrier goes up substantially. That may well be true, but of course, even if we do that transfer, in this case, we still have to displace olefin. So this is going to, again, require an associative displacement. Okay, so let's talk about copolymerization of ethylene with polar vinyl monomers. These are all commercial materials. Ethylene, acrylate copolymers, ethylene copolymers of this acrylic acid, ethylene copolymers of this trialkoxysilane. These are all copolymers. The advantage here is that, for example, in this case, and I'll say something about that later, you can cross-link this material and generate very, very tough cross-linked polyethylene. In this case, you can generate the salt here and cross-link these through a divalent cation. For example, the covers of golf balls involve these cross-linked materials via this carboxylic acid group. These materials have different barrier properties. So these are often used for food wrappings. They have higher barriers for oxygen permeability. So there are other copolymers here that have different applications. The early metal systems are incompatible with these polar functional groups. So these systems are generally made through radical initiation. And so you get low density polyethylene type structures, highly branched structures. Now, one of the problems, or the couple problems here, one, this requires extremely high temperatures and very high ethylene pressures. Two, you don't really have much control of the microstructure. You kind of take what you get here. So this is an opportunity for late metal catalysis, since we know that late metals are generally compatible with polar functionality. But it's not all that simple. So here are some problems connected with copolymerization of ethylene with vinyl functionalized monomers using late transition metal systems. Like the early metals, the metal center is pretty electrophilic. So in fact, it can bind the functional group more tightly than it binds the olefinic group, and basically quenches your polymerization. For example, this comes about with acrylonitrile. This simply binds through the nitrile and the catalyst is dead. There's also an issue of weak competitive binding. The metal center is electrophilic. If you have a bulky, fairly electrophilic olefin like methyl methacrylate, you simply don't compete with ethylene. This equilibrium lies far over to the side of the ethylene complex, and so you never generate enough of the olefinic complex of the polar monomer to propagate or to incorporate very much of that into your polymer. There's also an issue of beta elimination. If you do insert, and the functional group ends up beta to the metal center, you can get a beta X or beta G, as I show here, elimination to kill your catalyst. Rich Jordan and Usman Sen demonstrated this for vinyl chloride and vinyl bromide. Our group showed the same problem with vinyl acetate. The other issue is that we can generate a fairly strong chelate. So this comes about particularly with these vinyl esters. If that vinyl ester inserts, the ester carbonyl group coordinates back to the metal center, and then you're faced with displacing that interaction with ethylene to propagate the chain. And that equilibrium can lie very far to the side of the chelate. So I'll just show you how this works with methyl acrylate, and then move on to our study with the trialkoxysilane. So we'll talk briefly about copolymerization of ethylene and methyl acrylate. It turns out you can do this. So you can take one of these palladium species and copolymerize ethylene and methyl acrylate. You can use, if you use a lot of methyl acrylate, you can get up to 6 mol% incorporation into the copolymer, but the turnover frequency is quite low. And one of the reasons for this, so this is very slow. It turns out you can see this pi complex by NMR at -80. You can watch it undergo migratory insertion. It migrates to the beta carbon. This forms a 4-membered chelate. Palladium walks down the chain to make a 5-membered chelate, and then further to make a 6-membered chelate. And this is the catalyst resting state in the copolymerization of ethylene and methyl acrylate. So here's the overall picture. We're growing a chain. We bind methyl acrylate and inserts in a 2-1 fashion. That barrier turns out to be lower than ethylene insertion barrier, which is not surprising. It's kind of like a Michael addition. This is activated towards migration of the sort of the anionic alkyl group, if you like. We generate the resting state, and then we have an equilibrium between the resting state and the ethylene complex that's going to then undergo migratory insertion with a barrier of about 18. We start growing a chain, and then as soon as it binds acrylate and inserts, we're back to the resting state. So let's look at the siloxane, the trialkoxysilane, and show you some fairly recent results on that. Why would we want to make this material? This is a commercial material, and it's either made by grafting the siloxane onto preformed polyethylene, or it's made by radical copolymerization of ethylene and a vinyl trialkoxysilane. Maybe you've seen this material. If you look at your hot water pipes, it's probably, if it's plastic, it's certainly probably PEX, so-called PEX B. If you take this polymer and expose it to generally steam, you generate the, you clip off the ether groups to generate these silanols, and then these cross-link to make siloxane linkages. And this material then is quite impervious to, it's cross-linked polyethylene, quite impervious to further hydrolysis by water. Or you can also, this has been used to bind these polymers to surfaces. So we decided to take a further look on this, and so I'll show you some mechanistic work that turned out rather nicely. DuPont, we collaborate with DuPont on a lot of this chemistry early on, and they did some early work in this area, and we followed it up with a lot of further mechanistic studies. If you copolymerize ethylene and this triethoxyvinyl silane with this palladium complex, this palladium methyl nitrile complex, you make the copolymer. This is 100 psi ethylene at room temperature. You make the copolymer, but if you look closely, you also see butenes, one butene, one hexene, and one octene, and maybe a trace of the C10. If you look at the turnover frequency, as we increase the vinyl triethoxysilane, the turnover frequency drops, but not precipitously. And if you also calculate in the alpha olefin products, the turnover frequency actually stays basically the same. As you increase the vinyl triethoxysilane, you see more alpha olefin product. And of course, the incorporation tracks the concentration of the vinyl triethoxysilane. You get highly branched materials, and the molecular weight drops as we increase the vinyl triethoxysilane concentration. And if you look closely at this material, you get one terminal silyl group per chain. So we're only getting one trialkoxysilane group per chain. So how is this working? Well, again, if you take the methyl ether complex and expose this to trimethoxyvinylsilane, you can see the pi complex, and then you can watch this undergo migratory insertion at about -50 to generate the chelate. It's exclusively a 1,2 insertion product. This is a fairly weak interaction. The barrier to rotation around this silicon carbon bond is about 11 kilocalories per mole. The insertion barrier is a little over 18, which is very close to the ethylene insertion barrier, just about a half a kilocalorie difference in insertion barriers. So the vinyl trialkoxysilane inserts with about the same barrier as ethylene. Now, if you take the chelate and warm this up to -25, you see beta-silyl elimination. So you generate about a 90-10 mixture of the chelate and the propylene silyl complex. If you expose this equilibrating system to acetonitrile, propylene is displaced to generate this silyl nitrile complex. So that suggests we can get potentially chain transfer by beta-silyl elimination. And so if we take our chelate now and expose it to excess ethylene, this chelate opens extremely rapidly. So unlike the case of the ester, where the chelate was very difficult to open with ethylene, this opens like a shot at -78, and the equilibrium lies way over on the side of the ethylene complex. And we see a major complex in which this chelate is simply opened and we trap ethylene. We see a minor complex where the C3 unit is linear. Now, if we warm this to -60 degrees, everything converts to the minor isomer. And so that must be a case where silicon beta eliminates to give the propene complex and re-adds to generate the linear structure. If we warm this up to -40, propylene is eliminated. Remember, we're in the presence of excess ethylene. Propylene is eliminated, and we end up with this ethylene complex with a C2 linker. So silicon must basically chain walk back to this species, beta-silyl eliminate to generate the propylene complex. Ethylene displaces propylene, just as in the previous case, nitrile displaced the propylene species. So So imagine now we're here at this species I showed you on the previous slide here, where we have a C2 linker in the ethylene complex. If this beta-silyl eliminates, and we're in the presence of excess ethylene, this simply traps back. So this gets us nowhere. If this undergoes migratory insertion, we generate a C4 linker here. We've inserted ethylene into this bond and trapped with ethylene. If the silyl group runs back to the beta position and beta eliminates, we generate a propene complex that can be displaced with ethylene, and we're back here. So we've generated an equivalent of butene. Okay. If this further inserts ethylene, now we've got a C6 chain here. If silyl runs back to the beta position, beta eliminates, we generate a hexene complex. Hexene can be displaced with ethylene, and we're back here. But as this chain gets longer and longer, we are no longer able to access the beta-silyl complex through chain migration. The competition is such that before it reaches the beta position, we insert another ethylene, and so on. So once this chain gets long, we simply are inserting ethylene. So now imagine we're at this A species here where we've grown a chain and we've got the silicon group on the terminal position. So here we are growing our chain, and then it gets trapped by the trialkoxysilane. We do a 1,2 insertion. We beta eliminate silyl. The unsaturated chain drops off. Now we've made a polymer with the silyl group on the terminal position. Remember that P star was a polymer with the silyl on the terminal position. We trap that with ethylene. We insert. Now we're back at our resting state, and then this simply propagates. Okay, so we have comparable activity to homopolymerization, essentially the same activity as we see if we incorporate the alpha olefins in the calculation, and we see one terminal silane group per chain, and we get low molecular weight copolymer. And as we increase the silane concentration, we trap this species sooner and sooner and cut down the molecular weight. So that's the overall mechanistic picture of this copolymerization. Now I see that I'm running out of time, so I'm going to just say that in the case of nickel, we don't see the beta-silyl elimination. We can grow fairly high molecular weight copolymers. We get plenty of silane in for cross-linking purposes. In this case, we've got about 26 silyl groups per chain and a molecular weight of about 45,000. The homopolymerization is about 10 times faster than the copolymerization, and the chelate is the resting state. So there is a small issue of opening the chelate with ethylene that reduces the rate. So I'll go through I'll go on to the conclusions here, since I think I was supposed to speak for 40 minutes and we're at 45. So here are the advantage of the vinyl alkoxysilane comonomers in these late metal polymerizations. The insertion barriers of the vinyl alkoxysilanes into the palladium alkyl bonds and nickel alkyl bonds are similar to the ethylene insertion barriers. The chelates that result are readily opened with ethylene, unlike the ester case. The open chelates readily insert ethylene. And one experiment I didn't show you, the relative binding affinities favor ethylene, but it's not by prohibitive extent. At room temperature, the KEQ is roughly a factor of 3 or 4. So it's not it's the relative binding affinities, as in the case of methyl methacrylate, is not an issue. So I'm going to leave time for some questions. I'll stop there and just show you a few people that did the work. The last mechanistic studies were done primarily at Houston by Zhou Chen. Early work was done by Mark Leatherman and Wei Jin. A lot of the early work with the diimine systems were done by this group of folks here. And we've had funding from NSF and Welch and UH. So thanks a lot. I hope feels funny talking to no one, I have to say. I hope you're all out there still. So I'll stop there. Do I need to do anything to stop?
No.
Good.
Thank you very much, Professor Brookhart. So next we'll have a 5-minute discussion in break-up rooms. So people will talk about what they learned and what they want to ask in the small room. And Julio will help us to break us into small rooms. So you don't have to do anything.
I don't have to do anything.
Yeah, and then 5 minutes later, we'll come back and people, whoever has questions, then we'll ask. So does anyone want to start? Any questions from the breakout rooms?
So in my breakout room, we had a nice discussion, and I think Rong has a nice question or two for Professor Brookhart. So Rong.
Hi, thank you, Jeff. Thank you, Professor Brookhart, for the wonderful presentation. And oh, sorry,
there you are.
My camera now. So I have a question towards. So what is your comments towards the directly synthesis the functionalized polymers versus the post functionalization of the commercial polymers?
I'm sorry, incorporating the functional group by copolymerization or post polymerization?
Yeah, post functionalized with the functional groups on those, for example, commercial polyethylenes.
Mm-hmm.
Yeah,
yeah, I haven't. In the case of the vinyl trialkoxysilane, I think commercially it's done both ways. In both cases, you're using the vinyl trialkoxysilane. I would have thought that it might be easier to copolymerize, but I guess the engineering is such that it's done by post-polymerization. One of the issues that we had with the copolymerization, and I don't know whether one runs into this with this in industry or not, obviously have solved the problem. The materials are very sensitive to moisture. And so if you're not careful, when you do the copolymerization and isolate the polymer, the thing will cross-link on you. And then once it cross-links, you're in the soup. You know, you got a hunk of stuff that's can't be molded or at all worked with. So that could be one issue that the with the post polymerization process, you avoid pre cross-linking, as it were. So that's about all I can tell you. It's really hard to read the patent literature and really get an idea. In these commercial processes, no one publishes a lot of detail and goes into exactly what the problems are, and you really have to be on the inside to know that. So I can't give you a very good answer on that, unfortunately, but that's a good question.
So if you don't mind, maybe I can also present the question we discussed in our breakout room.
Yeah, sure, please go ahead.
So Brooke, I'm actually a solid state chemist, so I don't study molecular materials often. So I'm curious, when a polymer chain gets to the range of 100,000 to a million monomers, they're no longer particularly soluble. And we were actually curious, what is the best way to study the molecular structure, particularly with only a single catalyst at the end, for instance. We are curious how to be sure, or what is the best way to study the molecular structure of such a
I guess the best way is to make lower molecular weight material. But that's partly a joke, but you can induce chain transfer various ways. So if there's a severe solubility problem, you can make lower molecular weight materials that will be soluble. So you can look at microstructure and so on. Yeah, once you get to very high molecular weights, I mean, we have these catalysts that are basically, if you build in a lot more steric bulk, axial steric bulk, we've made sandwich compounds, and these things just don't chain transfer. And so we've made materials up to about 3 million, and we can, with dichloro benzene at very high temperatures, we can get enough in to get a GPC and a molecular weight. But once you get up to 3 or 4 million, we just can't analyze them. We know they've got to be linear based on the lower molecular weight materials. They got to be linear polyethylene. But as you say, once you get up in that range, the ultra high molecular weight materials, that's hard to analyze. I think these bulletproof vests, somehow they pull ultra high molecular weight. I think they use something like sulfuric, and they pull it out somehow and make fibers. And these fibers have incredible strength of this ultra high molecular weight polyethylene. But that it is, you're right. Once you get way up there, it's a severe problem in terms of trying to solubilize something and getting for example, an NMR spectrum of it. Hey, Jim.
Hey, Brooke. Great stuff. I really enjoyed it. One thing that we talked about in my breakout room was the sort of experimental techniques. I think for people that haven't done a lot of this, every time you show a number and a barrier, those are all experimentally determined. And,
that's right. Yeah.
And by NMR spectroscopy, if I understand.
That's right. Yeah.
And remember it. Could you talk a little bit about the techniques that go into that?
Yeah. So, for example, in the palladium systems, for example, we could generate, for example, we could make the dibutyl system, the diimine palladium dibutyl, which would be neutral, right? Then we put it in methylene chloride, and we add an equivalent of H-barf. That protonates off one of the alkyl groups. And so now you've got the palladium butyl system free of other insertion products. So then we can, and all this is at very low temperature, then we can watch by NMR, we can watch by dynamic NMR, we can watch the palladium run up and down the chain. Then we can trap it with ethylene to see whether we've trapped the secondary species or the primary species. So most of this work we do in methylene chloride or even CHD, the chlorofluorocarbon, which we can get down to -120, and the barf salts are still soluble. So it's tough work, but you can get well-defined species. If you make the dihexyl, you can protonate off and then see the C6 agostic and watch it run up and down the chain, trap it, and so on. So that's That's how we do it. You can make the nickel methyl ether complex, dissolve it in, again, methylene chloride or fluorinated version, add ethylene to it, and see the methyl ethylene complex, then watch it do migratory insertion and trap and make the propyl ethylene complex. So it's all low temperature NMR and kinetics. And we can correlate that with of course, the benchtop turnover frequencies that you can easily measure. So
Right. Very cool.
how you doing, Jim, up there? Did you get any snow this winter?
A little bit. It's mostly disappeared.
Has it disappeared?
We might get up to 60 tomorrow.
Oh wow, you're
Balmy.
moving along. Spring is only a month away.
Yeah.
Okay, any other questions from any of the audience?
There are a couple hands up. Jeff and Jada both had their hands up.
Oh, am I supposed to do something?
Hi, Brooke.
Hey, Jeff.
I really enjoyed your talk. It's a pleasure to hear you speak always, and I learn so much all the time. And this time I was struck by the end. We were talking about the vinyl silanes and how they can do beta silo elimination and maybe even silo eliminations when the silicon group is a little bit more remote. I was thinking about, could you use that process to make higher olefins rather than polyethylene? So you can take advantage of that beta or higher order silicon elimination, and then you can make maybe higher olefins from ethylene rather than polyethylene. And it would be catalytic in silicon then, if that were true.
Yeah, you might be able to figure out how to do that. Yeah. It probably is not going to compete with just doing it by standard adjusting the structure so you get beta elimination competitive with insertion, but yeah, you could probably do that.
Oh yeah, I also.
Hey, Brooke.
Yes.
So it's an incredible talk. I learned a lot from this, and thank you very much for the wonderful lecture. So my question is that you mentioned there was this incorporation of this functionalized alkenes or olefins, and there was a problem about the catalyst binding, and you showed that there was this very interesting structure where the polymer can basically bind back to the catalyst, right? Form a cyclic structure, at least as an intermediate. So I was I was wondering if that's although this could be a problem for synthesizing linear polyolefins, but would this be something that you can use to generate a cyclic polymers, like a macrocyclic polyolefins or something like that?
I haven't thought about it. The way maybe to do that is to start out with an alpha omega olefin. So you got olefins on both ends. And so if you had the right chain length, that dangling olefin could come back and insert, right? And make a new alkyl, and then that species could propagate, and when it inserts another diene, so you could end up with cycles in your chain. I I think it would be tricky to find a way to make a large, huge macrocycle. I haven't thought about it, but maybe it's possible.
Well, I think the size of the cyclic structure might be dependent on the feed ratio between ethylene and this functionalized pendant alkene, right? So if you have a very low ratio of this pendant alkene being incorporated,
Yeah,
you might be able to form a very big cyclic structure.
yeah, maybe. Possibly.
Thank you.
I think that's the end of our question section, right? I don't see any hands up anymore. So thank you again for Professor Brookhart's talk. And we would like to stay in the same room for social hours with the students and faculties in our center. So faculty and students from CIC, please stay on, and Professor Brookhart, please stay in the same.
Stay in the room. Okay, I brought my red wine for the social hour. So you guys in California, it's a little early, but I'm gonna start off here. Cheers.